Chemical bonding. Chemical bonding. This is a topic which we cover as our last topic in grade 11. Grade 10. Grade 10. Chemical bonding. A chemical bond is a force that attracts, or a force of attraction between between atoms. There may be two, there may be three, there may be more, but a chemical bond is a force of attraction between atoms. There are three main types of bonding: covalent, ionic, and metallic. Between the three, covalent is the strongest, followed by ionic, meaning metallic. Chemically, metallic is weak among the three compared to the three. The appearance of matter, texture, and physical properties are as a result of chemical bonding. Therefore, everything that you see, everything that you touch, everything that you stretch, everything that you differentiate in terms of color, it's all based on how it's bonded chemically. Texture, physical properties, they all are dependent on chemical bonding. Covalent bonding is our first one there, also known as molecular bonding. Involves sharing of electrons by non-metallic elements or atoms, resulting in the formation of molecules. That is why it's called molecular bonding. In the previous videos, we did define what a molecule is under the video where we looked at the atom. Molecule or molecular formula can be represented in three main ways. Molecular formula, structural formula, and atomic diagrams. Therefore, molecular bonding or molecular compounds can be expressed or represented in three ways in terms of how you can write them, how you can represent the compound. First is by using the molecular formula or formulae for plural, then structural formula or formulae, and atomic diagrams. The covalent bond is represented by a dashed line in the structural formula, and each dashed line represents a pair of shared electrons or the bonding electrons. Lewis dot and cross formulae are also used, showing only the valency electrons. The electrons in the Lewis dot and cross formulae are not part of the bonding pair. I repeat that the electrons in a Lewis dot and cross formula that are not part of the bonding pair are called non-bonding pairs or lone pairs. I have an example there. Our first example is of chlorine, which is from group 7. It's number 2 in their group, just below fluorine, and below chlorine there's bromine or bromine. Therefore, I'm only showing the outermost shell electrons known as the valency shell electrons. Chlorine bonds with itself, like in this case here, as a gas to form a molecule of chlorine, whose molecular formula is this. The atomic structure will be this, the Lewis formula will be this, and then the structural formula will be this. So I'm showing four formulas here: atomic diagram or atomic structure, the Lewis formula, the structural formula, and the molecular formula that I've not written here. These electrons, they are not part of the bond. There is only one pair being involved here, and it's represented by a dash here. Therefore, these electrons not involved in the bonding are referred to as the non-bonding pairs, and these are the ones that you refer to as the bonding pair. I've used crosses and dots just to differentiate and for us to trace which electron is coming from which atom. Coming to Lewis formulas, when you're writing Lewis formulae, you have to make sure that the shared electrons are placed like this. Do not place them horizontally. Let them be vertical like this, so that they belong to both atoms. They're being shared, and these two electrons are represented by a dash. So this is just one bond, one single bond, one pair of electrons being shared by two non-metallic atoms belonging to the same element. Therefore, they bond to form what we call a homonuclear compound. Homo means same nucleus compound. Therefore, that's a molecule of chlorine. Carbon 4 oxide, also known as carbon dioxide, that's our atomic formula, our atomic structure, the Lewis formula, the molecular formula, and the structural formula. Okay, my picture here is a little bit blurry, but it's clear. So here we've got the non-bonding pairs. We only show the outermost shell electrons. Check out these electrons. Here there are 4, and there are 4. The crosses are representing electrons from carbon, and the dots are representing electrons from oxygen. Therefore, meaning these are two pairs, meaning this is a double bond, and even here this is a double bond. Carbon has bonded with two oxygens to complete its outermost shell to have 8 electrons, and oxygen is having 1, 2, 3, 4 plus these 4, giving you 8 as well. Therefore, they have bonded to simply complete their outermost shells and become chemically stable. In the Lewis formula, look at the way I've written them. They are also being shared by both atoms. They are in between both atoms. They are horizontally. And I've also shown to say every X is paired with a dot, showing that one from carbon, one from oxygen. X from carbon, dot from oxygen. This is a double bond, and this is a double bond. The molecular formula is something like that. Then the structure formula, which involves the dashes representing bonds, is or can be written like that. Moving to this next slide, we've got water, also known as hydrogen oxide. That's our structure formula. Two pairs of lone pairs from oxygen, then hydrogens, then there's single bond there, or single pair. Okay, single shared pair between hydrogen and oxygen. Therefore, one oxygen is bonded to two hydrogens. That's our atomic structure. That's our Lewis structure, our molecular structure, and our structure formula. The correct way of writing the structure formula is like this, where you get to show even the the non-bonding electrons. This one, I've seen this one, but I would really reserve this. The best one is this, where you get to show even the orientation of the hydrogens, which show the repulsion forces between the electrons around the oxygen, because like charges repel. Properties of covalent compounds: they do not conduct electricity. Reason: they don't have free moving electrons. The electrons in the bonding structure is actually or are fixed. They're not free to move about. Number two, have low densities. Mainly it's because they're made from non-metallic elements. And the third one there is have low melting points. They act as insulators of heat. Exist as solids, liquids, and gases. Therefore, they exist in all three states at room temperature and pressure. Then the last property there is covalent liquids. Covalent liquid compounds do not dissolve ionic solid compounds. An example would be cooking oil doesn't dissolve sodium chloride or salt, table salt. Table salt doesn't easily dissolve in cooking oil, and the reason is because they do not interact. Cooking oil, which is a perfect covalent compound, doesn't have any significant charges in its molecules. Therefore, it doesn't really cause the sodium chloride, which is made of ions, to dissociate. Because there's a difference between dissociation and dissolving. Although they have used the word dissolving, but there's a difference. Giant molecules. We're still under covalent compounds. These are giant covalent compounds which include diamond, graphite, and silicon dioxide or silicon 4 oxide. Diamond and graphite are allotropes of the element carbon. The third allotrope is amorphous carbon. To be amorphous also means to be non-crystalline. An example of amorphous carbon is coal or charcoal. Allotropes are two or more forms of the same element in the same state. Therefore, diamond and graphite are both made of carbon atoms, but these carbon atoms are bonded differently. Therefore, they appear differently, but they are both in the same state. They are both solids. In each, atoms are arranged differently. I think I've just said that. Diamond. A crystalline carbon allotrope in which each carbon atom is bonded to 4 other carbon atoms. That is very key. Carbon here is bonded maximally. Carbon has a valency of 4. It comes from group 4. Therefore, it bonds to 4 other carbon atoms. Because of that kind of bonding, diamond appears the way it appears, and it has the properties that it has because of the way it is bonded. For example, it has a very high refractive index. Okay, it can bend light uniquely, making it appear or glow, or causing light to be reflected uniquely, and that is so interesting to us, and we tend to buy diamonds at very high prices because of that, but it's all because of bonding. Carbon is tetravalent. I've already mentioned that, has a valence of 4, and all bonding electrons are in bonds, not free. Therefore, in diamond, all the 4 valence shell electrons are actually involved in bonds. Properties of diamond: it's the hardest natural substance. Does not conduct electricity because there's no free electrons. Remember, covalent compounds, no free electrons. Allows light to pass through, therefore it's transparent. High melting point and insoluble in water. Mostly used in jewelry, okay, rings, neck chains, and the like. Used in drilling machines at the tip of the drill shaft because it's very hard, therefore it can drill in almost any rock. Used in cutting tools, for example, the glass cutter. Some glass cutters may have diamonds at the tip. Graphite, a crystalline carbon allotrope in which each carbon atom is bonded to only 3 other carbon atoms. Diamond, every carbon atom is bonded to 4 other. In graphite, 1 carbon atom is bonded to 3 others. This leaves 1 bonding electron in each atom free or delocalized. Properties: soft and black in color, can effectively conduct electricity due to free electrons. How do these free electrons come about? The way graphite is bonded. Composed of layers held by weak intermolecular forces, not covalent bonds but just weak intermolecular forces. Insoluble in water, just like diamond. Uses as a lubricant in machines because it's made of layers. Okay, because it's made of layers. Used in pencils. Okay, the pencil tip, the pencil center part of the pencil, the one that's used to write. Okay, that's actually a very perfect example of graphite. And also in DC motors and DC generators. In DC motors, you find brushes that are made of carbon. Those are the structural appearances of the two. There we have graphite, there we have diamond. The layers in graphite and the connectivity in diamond, and a few of the properties that some of them I didn't even highlight them there, like the downness, brilliant, basically those are the appearances or the physical appearances of the two allotropes. Silicon 4 oxide, aka silicon dioxide, also called also called silica, with the molecular formula of CiO2, though it's actually a continuous crystal, but it has got that formula because of how the two atoms, or how silicon would bond with oxygen if they were to just react in fixed ratios. Silica is a crystalline covalent compound in which each silicon atom is bonded to 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms. We should take note of how these atoms are bonded. In carbon, in diamond, carbon, 1 atom bonded to 4 others. In graphite, 1 atom bonded to 3. And here, every silicon atom is bonded to 2 oxygen atoms. Properties: silicon dioxide does not conduct electricity. It's typical of covalent compounds, apart from graphite, which has got a free electron or free electrons. Has a high melting point. It's very hard. Has a high density. Okay. Uses in water treatment as sand beds. In the making of glass, it's a source from which silicon is extracted to make semiconductor devices. Therefore, sand is mainly silicon dioxide. Okay, sand is mainly silicon dioxide or silicon 4 oxide. That is why here I've just said sand beds. In fact, oxygen is the most abundant element. Then silicon is number 2. Okay, it's number 2. Then number 3 is aluminium. Okay, and the reason why oxygen and silicon are most abundant is because of the abundance of sand in the world, the abundance of grains of sand on the beaches and in the oceans and rivers. Sand is so abundant, and sand is mainly composed of silicon 4 oxide. Altogether, we've got diamond there, the connectivity in diamond, silicon dioxide here, that's the connectivity, that's silicon bonded to oxygen atoms, and then that's a layer of graphite, and that's also graphite there. These are the weaker bonds, therefore weak force between layers, and then strong bonds between carbon atoms there. Dative bonding. We're not yet done with the covalent bonding. A coordinate or dative covalent bond involves a shared pair of electrons that come from a single atom. Examples are in the formation of an ammonium or hydronium ions. Okay, in both, an electron pair from either nitrogen or oxygen is used to bond with an electron deficient proton, respectively. I've got the examples there. I just took a picture of these. Therefore, ammonia plus 1 hydrogen proton there gives you ammonium. this has no electrons and it's just one atom. Okay, hydrogen has one electron, so when it loses that electron it forms a proton. That's hydrogen there. So this is typically a proton. It bonds with an ammonia molecule to give you an ammonia molecule to give you an ammonium ion. Therefore this is I would say the structural formulas of the whole of how the bonding takes place. Therefore ammonia plus one proton gives you ammonium. Since this hydrogen doesn't come with any electron, it actually increases the number of protons in this balanced molecule. A molecule is a group of stable atoms. Therefore if they are stable, means they are stable chemically to a greater extent and electrically. Therefore here there is no charge, and if you add a proton which has a charge, this is the surplus single charge, meaning an extra proton has been charged. Therefore it gives you or forms an ion. In a structural formula of a molecule formed from or an ion formed by dative bonding, the species which didn't donate the electrons, the species which is sharing electrons that it didn't donate or it didn't contribute, is always shown by an arrow, meaning nitrogen has shared its electrons with hydrogen. Same here, water, hydrogen gives you this kind of an arrangement. Anhydronium ion, this is the hydrogen who is sharing the two electrons that came from oxygen, covalently bonded, but resulting into excess protons. Therefore you've got that charge there. The equation is water plus this gives you that, and this is how actually acids dissociate. They form hydronium ions, not just bare protons like that. They are usually in this form. Intermolecular forces. Intermolecular forces are those forces that occur between particles, molecules, atoms, or ions. Okay, the strength of these forces at a given temperature dictates whether a substance will have the properties of a solid, liquid, or gas. The term van der Waals forces encompasses all types of intermolecular forces. All intermolecular forces arise from electrostatic interactions governed by the basic rule that like charges repel and unlike charges attract. In a molecule or in an atom, electrons orbit the nucleus. As they orbit, the region where the electrons accumulate in one fraction of a second becomes more negative than the region where they came from. Therefore, the region where they come from remains the region where they come from remains relatively positive. So during those moments, the shifting of charges as electrons orbit atoms or nuclei in a molecule and atom brings about these these attractions and repulsions in a substance. Therefore these forces are what we refer to as van der Waals forces. They can be classified in many ways, but they are a result of electron clouds shifting in bits. Hydrogen bonding, one of the interparticle type of bonding. A hydrogen bond is an attractive interaction between a hydrogen atom that is bonded to a very electronegative atom like oxygen, nitrogen, or fluorine, and an unshared pair of electrons on another electronegative atom. Okay, you can still read that through. Diagrammatically we have this is water and that's water. The electrons surrounding oxygen are simply more attracted to oxygen. What I'm trying to say here is in the bonding of this kind of a compound, the shared electrons are not 100% equally shared because of the differences in the degree by which the atoms attract the electrons. Therefore in this water molecule, the electrons are more attracted to oxygen. Oxygen has a high electron affinity and electron liking. Therefore electrons are closer to oxygen, giving oxygen a partial negative charge and hydrogen a partial positive charge. Therefore remember, like charges repel and like charges attract. Therefore these partial positive charges on the hydrogens get to be attracted to the partial negative regions of the neighboring molecules, creating what we call hydrogen bonds. Okay, so they are common. I'll give these two compounds here. They are common in water and common in nitrogen. Common in water and common in nitrogen. Even here, nitrogen is a little bit slightly negative because it attracts the electrons more in all its bonds. Therefore, it creates this partial negative region around it, and then the hydrogens in all other molecules are partially positive. Therefore, they tend to create this bonding, which is actually also a hydrogen bond. Hydrogen bonds can be quite strong. Okay, a single hydrogen bond is weak, but altogether they are quite strong. Substances that form hydrogen bonds have unusually high boiling points due to the extra energy that must be used to separate the molecules. The water molecule is the smallest molecule that has a boiling point too high for such a small molecule. This is because they are held by hydrogen bonds, and this is important, otherwise oceans would turn to vapor. Let me just pause there. Do you know why water is almost colorless? Let me just say colorless. It's because the water molecule is very small, and light can penetrate through very small particles. As a result, we tend to see through water to a greater depth. Unless the water is a lot, that's when you cannot easily see down there. You tend to see the bluish greenish colors. But the thing is, water is very small. A very small molecule with a very small molecular mass should be easy to evaporate, but it's hard to evaporate water compared to other liquids like ethanol. Ethanol is a large molecule, but its boiling point is 78 point something, while its water is 100 at RTP. Reason hydrogen bonding. Hydrogen bonding. When water is at its freezing point, it forms a crystalline ice structure or lattice in which the hydrogen bonds are extended, causing the molecules to space out, giving an increase in volume or expansion. At the freezing point, water forms a crystal because it's partially positive, partially negative. Remember, in the previous slide, I talked about these. Partial charges. Okay, this polarity. Okay, this is referred to as being polar. To be polar means the water has a region of positivity and a region of negativity. Therefore, because of this, during freezing, the molecules of water tend to interact in such a way that they form crystals that arrange themselves according to the laws of attraction and repulsion when it comes to pores. Therefore, water forms a crystal, and in the formation of the crystal, the water molecules push each other apart, leaving spaces in between them, causing expansion to occur. That is why ice has got a larger volume than water. As a result, the density of ice is actually less, making it or causing it to float on water. Note that polar compounds like water and ammonia are as such because of the uneven electron distribution in the molecule. The end with the greater negative field in the molecule becomes slightly negative, and the other end becomes slightly partially positive. Polarity of water, therefore, I think I've explained that already. That's the oxygen, high electron affinity. It attracts the electrons within the bonds more to itself, and then leaving the hydrogens partially positive, making it become partially negative because of the heavy negative cloud around it. Therefore, that's water. Okay, that's water, and just sort of putting this as to just trying to explain polarity a little bit. Ionic bonding. We're done with covalent bonding now. Ionic bonding. Chemical bond in which one atom transfers electrons to another. The metal usually gets to transfer the electron to the non-metal, resulting into charged particles or ions. Since they're charged, they are electrostatically charged. Therefore, this type of bonding is also called electrostatic bonding. The basic unit of an ionic compound is called the formula unit, not a molecule. A molecule is a basic unit of a molecular compound or covalent compound. Note, metals lose electrons and non-metals gain. Formation of magnesium fluoride. Magnesium has a valency of 2, so it will need 2 fluoride species to bond to. This is an atomic structure. Formula unit structure, not molecular, but formula unit structure, then the Lewis structure. Here, as you can see, the electrons are not truly shared the way I drew them in the other one. Therefore, they are somehow separate, but they are held together by their opposite charges. They are electrostatic charges. So here, as I'm writing, I could have even just written the outermost shell electrons, but I decided to write even the inner ones. And when you check, magnesium doesn't have the outermost shell because it's empty. It has lost 2 electrons from its outermost shell, to one to this fluorine species and the other one to this fluorine species, and that's the X we have there and the X there coming from hydrogen. An excess electron gives this a negative, and then the loss of 2 electrons means there will be a surplus of 2 protons here. So you have this, then this whole species will be bonded together by the opposite charges and they will form a unit, a formula unit, or in other words a compound. Formation of sodium chloride. Sodium here loses 1 electron to chlorine. Chlorine gains this electron around the dots, meaning coming from sodium. You can put the X and the dots anywhere, these are just meant to differentiate. The Lewis formula here, the sharing is not really like the way I drew it in covalent compounds, and that's your formula unit, not the molecular formula, but the formula unit, not the molecule. So they are held by these static charges, and these circles I'm putting here, they just you can still do without them, but yeah, these are just charges to show what they become, the type of ions and the charge they develop once they lose and gain electrons. Properties of ionic bonding: only conduct electricity when in solution or melted or molten state. Have high melting points. Most of them dissolve in polar solvents like water, yes, but they will not dissolve in perfect covalent compounds like cooking oil and other oils. Therefore, this should bring in our minds to say covalent compounds may not really be purely covalent, because atoms have got differences in the degree to which they attract electrons. Therefore, there are some compounds that are more covalent than others. Okay, there are some compounds that are more covalent than others, therefore in which the electrons are perfectly shared, and in others they're not perfectly shared, like water and ammonia. Most of them dissolve in polar solvents like water, form crystalline structures called lattices. Each crystal's shape depends on the type and size of the ions in its structure. They are mostly solids at RTP, room temperature and pressure. Metallic bonding, that's our last type. Defined as in the electron C model, a metal crystal is considered to be a 3-dimensional array of metal cations immersed in a sea of valence electrons. Keyword: valence electrons and cations immersed in a sea of valence electrons. The delocalized valence electrons are free to move through the crystal and are not associated with any one particular metal cation. The mobility of the electrons accounts for the high electrical conductivity of metals, including thermal, not just electrical but also thermal. Thermal conductivity can also be described to be the mobile electrons that conduct heat by carrying kinetic energy from one part of the crystal to another. 3-dimensional delocalized bonding allows the metal to be both malleable and ductile. That is why when you hammer a metal, it changes shape, because it's more like a sea. Okay, a sea. Water in the sea moves about. Therefore, when you push it, it will be pushed to one side. But metals are more like solid seas. You push, they will not really create waves like in water, but they'll change shape. The crystal lattice of metals consists of ions, not atoms, surrounded by a sea of electrons, forming a giant lattice. A diagram of a metal crystal. There you've got these valence electrons floating about. They float in such a way that they create this wave in such a way that where one electron leaves, another one approaches, to simply maintain the balance. And if this is a wire and it's connected to an EMF source or a source of voltage, these electrons would move in one direction. They would all move in one direction, but for now they are just moving about more like water in the sea. Properties of metallic bonding. There, to close our slides or our video here: high melting point, high density, malleable, meaning can be hammered into sheets; ductile, meaning can be put into wires; sonorous, like in bells; lustrous, yes, they are shiny when polished; and then they are good electrical and heat conductors. That marks our topic, or the end of our topic in bonding. Remember to subscribe and leave your comments below. Thank you very much.